Hello everyone, and welcome to the online lecture for college algebra. In this video, we're going to cover section P7 on complex numbers. So let's begin then by describing the set of complex numbers. The set of complex numbers is the set of all numbers of the form a plus bi, where a and b are real numbers, and I is defined as the square root of -1, which is not a real number. And so you can kind of think of it as broken up into two parts. So our complex numbers are numbers of the form a plus bi. The part without I, a, is called the real part of the imaginary number, or the complex number rather. And the part bi is called the imaginary part. I itself, the square root of -1, is sometimes called the imaginary number. So the imaginary part is the part with I in it. Now it is important to note here that there's no restriction in the definition that says that a and b can't be 0. In fact, they can. If b, for example, the imaginary coefficient were 0, then you would have a number a plus 0i, or just a. So real numbers are a subset of complex numbers. They're contained inside the set of complex numbers. Real numbers are specifically complex numbers with no imaginary part, with 0 for their imaginary part. And similarly, the set of purely imaginary numbers, like 3i, are also complex numbers. They're just complex numbers with 0 real part. And so the complex numbers are kind of a broadening of our sets. So complex numbers are sometimes written as a stylized C. The real numbers that we work with most frequently are inside of that set. The imaginary numbers are also inside of that set. So if you ever see any theorems in mathematics involving the set of complex numbers, which we have quite a few of, that means that those theorems also apply to the set of real numbers as well. Because in the end, real numbers are complex numbers, just complex numbers with 0 imaginary part. So a couple quick things to note about our complex number system, some terminology. The first is that a plus bi, this form that we're writing it in, is called the standard form of a complex number. There are other forms you can write complex numbers in. For example, if you end up taking Math 112 trigonometry, you'll learn that there's something called the trigonometric form of a complex number, which involves sines and cosines. And then the other thing, and this is a property we're going to make extensive use of, is that if I is defined as the square root of -1, then I squared would get rid of the square root symbol, and it would give you -1. So normally you can't square any real number and get a negative number out, but you can square an imaginary number and get a negative number out. What we're primarily going to be focusing on in this section, however, is operations with the complex numbers. And of course, operations are addition, subtraction, multiplication, and division. And for the most part, it's really straightforward, especially for the first pair of operations that we're going to look at, addition and subtraction. Because in the end, it's pretty much just combining like terms. Just like if you have a 4x and you wanted to add to that a 3x, that would give you a 7x. We treat I the same way. So if you have a 4i plus 3i, that would give you a total of 7i. So you basically combine the real parts of the complex numbers together, and you combine the imaginary parts of the complex numbers together. So with that said, try taking a minute to pause the video and see if you can find the solutions to example 1. All right, so for part A, the only thing you have to be careful about is distributing that negative sign through the parentheses. It should change the sign of both terms. So we've got a 6 minus 7i minus 3, and then that becomes a plus 4i. And then just combine like terms. For real part, we've got 6 minus 3, or 3. And for imaginary part, we've got a 4i minus 7i, which would give us a negative 3i. Part B is similar. So because of the addition in the middle here, the parentheses are really not contributing anything at all, so I'm just going to drop them. This is 5 plus 3i root 5, and that's going to turn into a minus 4 minus 5i root 5, and then just combine like terms again. Now it's important to note that this 3i root 5 and this minus 5i root 5 can only combine together because the radicals are exactly the same. So essentially we're treating I root 5 like our variable in this example up here. So for the root part, or rather the real parts, we've got 5 minus 4, so that would just give us 1. We've got 3i root 5 minus 5i root 5, which would give us a negative 2i root 5. So if this had been, say, 3i root 3 and a minus 5i root 5, so the radicals had been different, then at that point you would just have to leave it as two separate terms because you can't add square roots that way. The other thing to note here is that what you see written here, the order that the terms are in, are common. This is the way we handle imaginary parts that involve radicals. We always put the I in between the real part and the root. So technically, if you think of this as the form bi, b, the coefficient, is 5 square roots of 5. So if you wanted to turn this into a decimal, we could plug this into a calculator, and let's say we just round to one decimal place right now to keep it simple. This would be about 11.2. So this is about a minus 11.2i. So you might think then, if we're writing in standard form as bi, why do we not write 5 square roots of 5 times I? And the truth of the matter is, we just want to make sure that there's no confusion about whether the I is in the square root or not. So to make sure of that, we just move the I up to in front of the square root. And so you'll always see it written this way. If there's a radical, that will always be written at the very end of the term. Next up, we've got multiplication. This one is also pretty straightforward as long as you remember that fact from the earlier slide that I squared is equal to negative 1. So anytime you see an I squared in your final answer, you should do that replacement because that will get rid of the I completely. Aside from that, you treat it again just like you would a variable. So if you had 3x times 2x, that would be 6x squared. Same thing with I. If you have 3i times 2i, that would give you 6i squared, but because I squared is negative 1, you could simplify that to just negative 6. Any i's that stay as I to the first power, we just leave them that way in the problem. So with that said, take a minute to pause the video here and see if you can find the solutions to parts A and B of example 2. All right, so for part A, this is simply a matter of distributing across the parentheses. So for the first term, we would have a negative 3i times 5. You can multiply the real numbers together. So that would give us negative 15i. And for the second term, we would have a minus 3i times a positive 2i, which would give us a negative 6i squared. All right, but because we've got an I squared, we're going to simplify that away. So we've got a minus 15i minus 6 times negative 1. So that minus 1 would make this minus a negative 6. So that's going to turn into a plus 6, but we want to write our answer in standard form a plus bi. So I'm just going to swap the order of the terms, and this would be the same as positive 6 minus 15i. For part B, we're going to have to FOIL this. So that's what we're going to do. So first terms, we'd have 3 times 2 or 6. Distribute the 3 through. 3 times 5. I would give us a 15i. Now I'm going to distribute the 7i through. 7i plus times 2 would give us a 14i, and then 7i times 5i, the 7 times 5 would give us 35, and the I times I would be I squared. All right, so once again, we're going to replace the I squared with a -1, and I'm going to go ahead and combine the I terms together as well. 15 plus 14 giving us 29i. And then this is a plus 35 times a -1, and you can drop this step once you get used to the fact that I squared just changes the sign that's in front of the term. So that would end up being 6 minus 35, which would combine to give us a -29, and then we still have the plus 29i. All right, a few more examples of multiplication, but now we'll also bring some more radicals into the mix. So with that said, try pausing the video here and see if you can find the solutions to part C and D of example 2. All right, well, once again in part C, we're just going to FOIL here. We just have a lot more roots this time around. So I'm going to start by distributing the square root of 2 through. Square root of 2 times itself is just 2. Then the square root of 2 times square root of 3, remember properties of radicals, would be the square root of 2 times 3, or 6. And this will be minus because it's the positive terms times a negative. So minus I square root of 6. Then I'm going to distribute the square root of 3 through. Positive I square root of 3 times a positive square root of 2. So that's a plus I square roots of 6. Those are going to cancel, which is no surprise because notice that these terms are just conjugates of each other. And then for the last term, we have a positive times a negative, so a minus square root of 3 times square root of 3 would be 3. I times I would be I squared. All right, so really all we need to do here is to simplify by replacing the I squared. So again, the middle terms cancel out. So this is a 2 minus a 3 times -1. So that becomes 2 plus 3. So we just get the real number of 5. No i's left to be found. Once again, this is a pretty important concept that we'll come back to a little bit later on. Notice that if you have a binomial with an I in it, if you multiply it by its conjugate, you end up with an expression without any i's at all left over. All right, so for part D, we've got the square root of 6 plus I square roots of 3 quantity squared. Please, please, please do not just square each of those terms. If you wrote this as square root of 6 squared plus I square roots of 3 squared, I would be very unhappy. Exponents do not distribute across addition and subtraction. This is a FOIL problem. Anything squared, by definition, is a number multiplied by itself, so we're just going to write it out twice and FOIL it. At this point, it becomes very similar to part C, although the signs in the middle aren't flipped this time, so those middle terms are not going to cancel out. So first, we've got square root of 6 times itself for 6. Square root of 6 times square root of 3 would be square root of 6 times 3, or 18. Another I square roots of 18. And then once again, square root of 3 times square root of 3 is 3. I times I would be I squared. So we just need to simplify this now. We've got a 6. 1 I square root of 18 plus another would give us 2 I square roots of 18. Square root of 18 itself also simplifies. I'll get to that in the next step. And then the plus 3i squared becomes a minus 3. So 6 minus 3 would of course give us 3. But now square root of 18, because 18 is 9 times 2. We can take the square root of the 9, and that would give us 3 square roots of 2. But because multiplication is commutative, you can multiply in whatever order you want to. We can multiply the 2 and the 3 together. So this is going to give us 6i square roots of 2. So we've covered 3 operations so far: addition, subtraction, and multiplication, meaning there's one left to go. But before we start talking about division, there is one variation on multiplication that we need to go into a little more detail on. Because all we've done so far is multiply 2 imaginary numbers together, or 2 complex numbers together. And so our biggest power of I ended up being I squared. But what if you multiplied 4 complex numbers together? You would end up with an I to the 4th power. If you wanted to, instead of squaring a complex number, cube it, you would end up with an I to the 3rd power. So how do we handle those higher powers of I, and do they still simplify? And the answer is yes, they will. So let's think this through then, and let's fill out the first 9 powers of I. So we know by definition that I to the 1st power is square root of -1, and then if you square that to get I squared, it would just cancel out the square root symbol, and we would end up with just -1. What about I cubed then? And from here on, we're going to start writing things in terms of I again, because that's how we would leave our final answer if we wanted to write it in standard form. So I cubed, you can think of as I squared times I, but I squared we know is -1. So I cubed would be the same as negative I to the 1st power. For I to the 4th, we can do something similar. There are 2 ways you could think about this one. You could either multiply I cubed by another I and simplify, or another way to think about this one is that I to the 4th is I squared times I squared by properties of exponents. And so if those are both -1, I to the 4th power would end up being +1. I to the 5th power would be I to the 4th times I, but if I to the 4th is +1, I to the 5th power is actually exactly the same as I to the 1st power. And so what you're going to find is that if you keep this pattern up, if you just multiply in an extra I each time, I to the 6th, you would multiply another I, and you would just get I squared, which would be -1 again. Then you would get -I, +1, +I. And so what happens is you get this pattern. And let me go ahead and rewrite this -1 back as I again, for the sake of spotting the pattern. A pattern of 4 numbers: I, -1, -I, +1. And you'll find that that same pattern repeats every 4 powers of I. And so what you'll notice is that anytime you have an exponent that is a multiple of 4, it ends up simplifying to just +1. So that's our first result here. I to the 4n is equal to 1, where n is any integer. So that's just a mathematical way of saying that if you take I and you raise it to a multiple of 4, you just get +1. So let's use that idea to create some higher powers of I without necessarily counting our way through the pattern all the way up to, say, 23, if we've got something like I to the 23rd. The trick is that you want to find the biggest multiple of 4 that doesn't pass the exponent that you're looking for. So I want the biggest multiple of 4 that is not bigger than 9, and you want to pull that many i's out of the expression. So if I want to evaluate I to the 9th, for example, the biggest multiple of 4 that doesn't pass that would be I to the 8th. So if I pull those out, I to the 9th you can think of as I to the 8th times I to the 1st power. But since we know any multiple of 4 as an exponent of I ends up being 1, that term always just goes away. And so it's just the I to the first power that we're left with, which is the same thing that we see down here in the pattern. So take a second to pause the video and see if you can use that same concept, that same strategy, to figure out what I to the 23rd power would be equal to. All right, so the biggest power of 4, the biggest multiple of 4 rather, that is smaller than 23 would be 20. So if we pull out 20 of those i's, that would leave I cubed left over. So that would then be 1 times I cubed or I cubed. But that we can simplify even further because I cubed is negative I squared times I, or negative 1 times I. And so no matter what power of I you're dealing with, you can always break it down into either plus or minus I to the first power or plus or minus 1. So this brings us then to our final operation with complex numbers, division. And this is the trickiest, but it's still just an extension of something we've looked at a little bit earlier in the course. Because remember, I is square root of negative 1. It is a square root. It's a radical, essentially. And so if you want to divide two complex numbers, it's actually the exact same process as rationalizing a denominator with square roots in it. So remember from sections P3 and P4 that if you want to radicalize, or excuse me, if you want to rationalize a denominator that has a binomial with a radical in it, you would multiply by its conjugate. We're going to do the same thing here. Treat it just like you would a square root. All right, and think about what you would do if you just had a single square root in the denominator. So with that said, try pausing the video here and see if you can simplify the answers to parts A and B. Divide these complex numbers. All right, so for part A, if we had a square root in the denominator, we would just multiply by that same square root. So that's what we're going to do here. We're going to multiply the bottom of this fraction by I, but that means we need to multiply the top of the fraction by the same thing to keep it balanced, keep the value equal. So I'm going to multiply both the top and the bottom by I. All right, be careful. That means it has to distribute through to both pieces of the numerator. So that's going to be a minus 3I minus 3I squared divided by I times I, or I squared. But remember, I squared is just negative 1. So if I replace those I squares with negative 1, that becomes a minus 3I plus 3 divided by negative 1. But dividing by negative 1 just changes the sign, just like multiplying by negative 1. But to be careful here, like always when you're reducing fractions, it has to divide into both terms in the numerator. So that's going to turn into a positive 3I and a negative 3. But this is not quite standard form yet. We still want the real part first. So I'm just going to swap the order of the terms and write this as minus 3 plus 3I. For part B, if we want to divide these two, what we're going to have to do is essentially rationalize the denominator. I want to multiply by the conjugate. So if it's 2 minus 3I, I want to multiply by 2 plus 3I. Whatever I do to the bottom of the fraction, multiply the same thing into the top. So now we have to FOIL. So in the numerator, we're going to have 8 plus 12I plus 4I plus 6i squared. In the denominator, these are conjugates. We're going to have 4. And then the middle terms are going to cancel each other out. We're going to have a plus 6i minus 6i. So those are gone. And then we have a negative 3i times a positive 3i, which would be a negative 9i squared. So if we replace the I squares with negative 1s, the numerator is now 8, and instead of a plus 6, this becomes a minus 6. So 8 minus 6, or 2. And then we can combine like terms. 12i plus 4i would be 16i. And then the denominator, instead of 4 minus 9, because of the I squared, becomes 4 plus 9. So we have a 13. Now this works as a final answer, and if you left it like this on an exam, I would be perfectly happy with that. This is not quite considered standard form though, a plus bi, because it's still all over 13 in this case. So what we're going to do is use properties of fractions to break this up. All right, you guys know how fraction addition work. If you have a common denominator, a over c plus b over c, you can just add the numerators together to get a plus b over c. You can also reverse the process. If you have addition or subtraction in the numerator of a fraction, you can break it up. So we can write this as 2 over 13 plus 16i over 13. And we can even go one step further than that, also by property of exponents. We know that if you multiply a fraction by a number, it goes in the numerator. But again, if we reverse engineer this process, we can actually take our I in the numerator and pull it outside of the fraction as multiplication. So you can even pull the I out of the fraction and write this as 2/13 plus 16 over 13i. And so now that is in standard form, a plus bi, where a is 2/13 and b is 16/13. All right, so we've worked all kinds of operations with complex numbers. Now let's take a look at how we work with square roots of negative numbers if it's not already written in terms of I. So the key idea here is that for any positive real number b, if you have the square root of a negative number, square root of negative b, you can just write that as I times the square root of the positive version of the number, I square roots of b. So in other words, what that's saying is that if you've got something like square root of negative 3, you can just write that as I times the square root of positive 3. Well, that's easy enough to show why that is, and it's the same way we simplify square roots. So square root of negative b is the same as the square root of negative 1 times b, but by property of square roots, right, square root of a times square root of b is equal to square root of ab. So if we reverse that process, this would be square root of negative 1 times square root of b, but square root of negative 1 is the definition of I. So it's basically separating out the negative sign and then taking the square root of it to pull an I out of the radical. There are some situations we need to be careful about though, and that's that you have to be very careful with the order that you perform these situations in. So I want you to consider as an example, square root of negative 2 times square root of negative 8. There are two different ways you can work this problem based off of the information we've covered so far. One is actually correct and one is incorrect though, so we need to be careful. So for the first way of tackling the problem, let's just directly apply the property of exponents, or the property of radicals, which is an extension of the property of exponents. So this is the square root of two numbers multiplied together, which means we should be able to do this as square root of negative 2 times negative 8, which would turn into the square root of positive 16, which, because 16 is 4 squared, would just give us 4. The other way that we could handle this problem is by applying this property up here first and pulling the i's out. So square root of negative 2 times square root of negative 8 would be equal to I square roots of 2 times I square roots of 8, which if you multiply that together would give you I squared square root of 16, which would give you negative 1 times 4, or negative 4. So you can see that we get two different answers here by a factor of negative 1, a positive 4 and a negative 4. So although both of these processes seem like they work, one is correct, one is incorrect. By using the property of exponents first and getting the positive 4, that is actually the wrong answer. That's not what you want to do. The negative 4 is actually the correct solution here. So the key thing to keep in mind is that if you don't want to make mistakes with negative signs, if you don't want to get your answer wrong by a factor of negative 1, always pull I out of the square roots before you perform operations. All right, so you can kind of think of it as like another wrinkle to the order of operations PEMDAS. The key thing here is that you always pull I out before you do anything else. So they kind of situate like parentheses in the order of operations. All right, so keeping that in mind, let's take a look at a few examples involving operations with roots of negative numbers. All right, so in example 5, we've got these roots of negative numbers. We want to write our final answers for these operations in standard form of a complex number, a plus bi. So with that said, try pausing the video here and see if you can find the solutions to example 5. All right, so for part A, we're going to simplify these square roots as much as possible. So the square root of negative 16 would be I square root of positive 16, but that would just be I times 4. So that's a 4i, and square root of negative 25 would be I times the square root of positive 25, which is 5. So that would be plus 5i. And because these are both i's to the first power, 4i plus 5i would give us 9i. For part B, we've got the square root of negative 5 cubed. So there are two ways you could honestly work this problem. You could pull the I out of the square root and then distribute the exponent through. So you could write it as I square roots of 5, and then by properties of exponents, write that as I cubed square root of 5 cubed. And that would certainly work. Or the other way is you could just remember that anything cubed is multiplied by itself 3 times, which is what we're going to have to do to simplify the square root anyway. So I'm going to write this as I square roots of 5 times I square roots of 5 times I square roots of 5. And for the reason that I'm doing that is I want to start by just multiplying two of them together. So I square root of 5 times I square root of 5 would give us I squared, and square root of 5 times itself would give us 5. But then this is still times our last I square root of 5. I squared we could also replace with negative 1, so this is a negative 5 times I square root of 5. And so because we picked out two of these to multiply together, we now have an I to the first power, which we can't simplify any further, and we have a square root of 5 that we can't simplify any further. So this is the simplified final answer. Anytime you're working with i's or square roots of any type, I is a square root, remember, it always comes in handy to multiply things in pairs, because pairs always simplify nicely. Whereas in this case, because we had an odd power, we had one left over. All right, and last but not least, we've got part C. The thing to be careful about here is that this is another one you would get wrong if you use properties of exponents, because you would be multiplying two of these negative square roots together, or rather roots of negative numbers together. So the first thing we want to do is to pull the I out. So this would be I root 6 times square root of 2 minus I root 3. And now we can just distribute through. So the first term would be I square roots of 12, 6 times 2. And the second one would be a minus I squared square root of 18, 6 times 3. So square root of 12, because 12 is 4 times 3, and you can take the square root of 4, would be 2 square roots of 3. This I squared is a negative 1, which would just flip the sign out front, so this is a plus. And since 18 is 9 times 2, that would be a plus 3 square roots of 2. So that's most of the work. The last thing I'm going to do is write it in standard form. I'm going to put the real part first. So this is 3 square roots of 2 plus, and then again, this is a little bit technical. It's not the end of the world if you forget this, but anytime we have a real number, a square root, and an I all multiplied together, it is common practice to write the I in between. So that would be plus 2I square roots of 3. All right, and so that is it for section P7. For the most part, this is a pretty straightforward section. As far as types of problems, you've got operations with complex numbers. I've broken that up into two parts here because addition, subtraction, and multiplication are all pretty straightforward and easy. There's not a lot going on. The only thing with multiplication is to remember that I squared is negative 1. And then there's also division with complex numbers. That's kind of its own thing. You basically divide complex numbers by, imagine it the same way you would as rationalizing the denominator. All right, and then last but not least, we've got operations with roots of negative numbers, and that's also pretty straightforward. The only trick is to pull the negative numbers out as I, and then it really becomes just problems number 1 and 2 again, operations with I's. All right, so with that said, if you guys have any questions, please make sure you let me know, and I will see you in the next video.